Today, let's take a look at one Leetcode problem. In this problem, we're given a list of positive integers and also a k. Our goal is to find out whether we can partition this list of integers into k disjoint partitions so that each partition has a sum that are all equal. So here is just one example. 5 numbers in k of 3. One way to partition it is this. So every partition has a sum of 3. So in this case, we return true. If we cannot find such a partitioning, we return false. So keep in mind that these numbers should be positive in this case. And also we should be able to find out what the target sum for each partition is, which is to get a total of the list and divide by 3. If this is not divisible, we can immediately return false. Otherwise, it is possible. One approach we can explore is using exhaustive search. It's almost like a depth-first search, and we can use recursion for that. For each recursive call, we take the next item from the list and try to find the first partition that can fit that number in there without exceeding the total sum, a limit. If we can, then we recurse down. Otherwise, we backtrack and try different assignment of that value to a different partition. So let's explore that using this example and see if we can go through that algorithm. So let's think about this. We can start with 3 empty lists. And when the first item comes in, we put that item in the first partition because now, since everything's empty, the sum should be smaller than 3. So this is good. The second item comes in, we put that item in the first partition as well, and so on and so forth. But since this problem only requires a Boolean answer, in the end, it looks like we don't have to keep track of each and every combination and exactly what are the items that are in the partitioning. We don't need that detail. So in that sense, we don't even have to keep the list of items of each partition. We just need to keep track of the total for each partition. We can start with zeros, and then we just keep on adding to it until we hit a limit. Then we have to backtrack. So let's take a look at that in how we run the recursion using and display that or represent that in our recursion tree. When we start, we have 3 zeros. This represents the sum of the partitions. The first item of the list is 1. So let's see which partition can fit 1. Of course, the first partition can fit 1. Now we keep on going to the next partition. So this is a recursion call represented by the dash. We keep on calling this function itself, and I'm going to talk about a base case later on when we progress further. So the next item is 1. We can add 1 again to the first partition. Now the total is 2, still less than 3. Next item is 3. We recurse down. Now the first partition cannot hold 3, of course, because that would be 2 plus 3 is 5, greater than 3. We try the next partition, which is 0, so 3 can fit into the next partition. Keep on going. The next item is 2. We're here. And 2 is not able to fit into the first and second partition, but the last partition. So which is good. Now let's try adding 2 to the next. Let's try adding 2 to one of the partitions. So here we are not able to progress any further since 2 is not able to fit into any of these partitions. So imagine this. Here is in this tree it's not represented, but you can imagine that we have one more recursion call with an input of 2 and the current situation for the partitions, and this will return false. And coming back to here, basically we have to try this again, and we realize that we're not able to put 2 anywhere else because this is already the last partition we just tried. So we have to fail this, return false back to here. So here we will have to try putting 3 into a different partition. So previously we put 3 in the second partition. Now we have to try putting 3 in the next partition available, which is the last partition. However, as you can imagine, because the next partition has a sum of 0, which is exactly the same as the previous situation, so this is going to end up the same. And once we put 3 into the last partition, the next item is going to fit into the second partition, and then we hit a dead end as well. So overall, this is going to fail this call here. So again, we backtrack. Instead of putting 1 into the first partition, we try putting 1 into the second partition here. So you get the idea. Basically, we backtrack, try, if we hit a dead end, we backtrack and try a different approach. So similarly to depth first search, we keep on searching for an item along one side of the edge, normally the left-hand side. And if we hit a dead end, we backtrack one step up and try the next route. Going down until we exhausted all the possibilities. So here, putting 1 into the second partition looks like it's going to work out, since now the next item is 3. We put 3 into 3 can only fit into the last partition. So keep on going. Next item is 2. We can put 2 into the first partition, and so on and so forth. Eventually, we end up with all partitions filled up, and we also don't have any items to work on. So that's when we hit our base case. So the base case is when we exhausted our list. So we declare true. Otherwise, we have to declare false. Before we get into the implementations, let's think about the complexity for this algorithm. Normally, we have to compute the complexity using our recursion tree. So we know what the fanning factor is, the branching factor is, and we compute that way. But here is a little bit less intuitive and obvious. But however, as I said, this is pretty much similar to assigning a partition number to each and every items in our list. So this is a simple combination problem. So each item gets k choices of assignment. We have n such items. That becomes k to the nth, which is exponential. So we know that at least we have to yeah, that is a little bit tricky. because later on we are going to do some optimization, but we know that our lower bound is our upper bound is exponential. And in terms of space wise, we know that the only space we're going to take is our cost stack, and the cost stack is going to go as deep as the number of items in our list. So that is going to be linear, big O of n in that case. So let's take a look at implementation. I'm going to use Python here, and let's just go over this quickly. So let's first take a look at the recursion part of the algorithm. So this is recursion, and we're feeding the index of the items in the list into this function. So this is telling the function that we are working on item at index I. So if we have exhausted the list, then we return true. Otherwise, we keep on going. We get the value of this item, and now we loop through the list of partitions and try to see if any partition can take that item. If the partition, the sum of the partition right now, add the value is less than the target value or target sum, which means that that value can fit into the partition. So we add the value to our partition, J, and then we recurse by searching for a partition for the next item in the list. If this search renders success, then we return true. Otherwise, we have to backtrack here a little bit. Backtrack by taking that item off of the partition, which is essentially subtracting that from the total. And the loop will keep on going and try the next partition for that item. If none of that is successful, we return false. So the caller, the wrapper function looks like this. We first do some sanity checks. These are the edge cases, basically. Div mod returns the quotient as well as the remainder. If we have a remainder that is not 0, we know that the partitioning cannot be done. Otherwise, we initialize the partitions to all zeros, and we start from the first item. In order to pass the Leetcode, checker, this one is not going to pass it. However, we can modify this and make some tiny adjustments to optimize this. First thing we realize is that we can start, if we can sort the original list and start from the last item, which are the larger items first, then we can we start from the larger items first, so that way we have we can fail early, basically. So let's just try doing that. First, we do a sort. We sort and we start from the back of the list. In that sense, we don't even have to put the index in there. So here, instead of getting the item from a position, we just do a pop. So pop is going to pop the last item from the list in Python. And here, instead of checking if we exhausted the list, we just need to check to see if the list is empty or not. If it's empty, we return true. And here, okay. So the backtrack part, now we have to throw that list back, throw that item back into the list. Right, so this is the backtrack part. So another optimization we can do is fail even earlier. Now let's sort the list up front. And then, as you can imagine, if the largest item, which is at the back of the list, the last item, if the last item is greater than our target, then we also return false. So which is obvious, if the largest item is already larger than the sum you're computing, then adding more items to it will just make it worse, right? Make the sum even bigger. So we can immediately know that it's not going to work. And also one thing we can optimize is here, somewhere here. As you can see here, when during the backtracking part, we mentioned it briefly. When we try putting 3 in the first partition that works, it's not going to work, and then we backtrack. Now in our algorithm, we blindly try putting 3 into the next possible partition, which is also 0, right? So we know that this will have the same effect of previous iteration. So here we can be a little bit smarter and not have to try putting a 3 into an empty partition again, because it would just have the same outcome. So in that sense, we can just, after trying this and we're ready to try the next partition, we can just put in a check real quick if part, which is the current partition sum, is empty, then we skip it. So this way, when we're backtracking 3, take that 3 off of this partition. We know that this partition is 0. There's no there's no need to try the next partition anymore. So that is it. This is going to pass our Leetcode checker, and I'm just going to briefly talk about the mistakes that I made when I worked on this problem. All of this happened to be from the solution. If you take a look at the solution tab, you will see this solution. But when I was working on this, I went down the recursion route. However, my recursion looks a little bit ugly. So the lesson that I learned is that really think hard of what the recursion should be. The recursion should be very simple. The recursion should just work on an overlapping but very similar problem, a subproblem, but overlapping. And in our case, the recursion is quite simple. Just getting an item from the list and try to find a partition that can host that item. If it works, then keep on going, do the same thing, call the same function again for the next item, otherwise backtrack. So when I was working on this, I did it the hard way. I first grabbed the next item and shove it into the one of the partitions. And then in the same function call, I try to look for the next item that can also fit into one of the partitions, which is I'm doing double the work basically without realizing that I'm redoing exactly the same thing as what the function is doing. So that becomes really ugly. Anyway, thanks for watching and good luck to your studies.